Welcome back to the deep dive. We've got a really fascinating stack of research today that touches on something physically sitting in almost every office.
Probably gathering dust in a closet somewhere.
Blinking away, exactly. We're talking about the network switch.
The humble workhorse of the internet. It's funny because in cybersecurity, we always focus on the flashy stuff, ransomware, phishing.
Yeah, state-sponsored hackers, yeah.
But this research forces us to look at the plumbing.
Exactly. And what stood out to me in these notes, and this is really the core theme today, is that we treat these things like appliances. You plug them in, they work, you forget them.
Right.
But the sources are arguing that this plug-and-play mentality is actually a massive security liability. They call it the open door policy of the networking world.
It's a perfect metaphor. We spend millions on firewalls building these massive castle walls.
Around the perimeter.
But inside the castle, we just leave every door unlocked. If you look at the default configuration of a standard Layer 2 switch, it is designed for connectivity, not security. It prioritizes uptime over lockdown.
And that's our mission for this deep dive. We're going to take this default open door architecture and figure out how to lock it down into what the source calls a fortress architecture.
It needs to be done.
And the stakes seem pretty high here. There's a line in the research that says physical access equals total compromise. Is that hyperbole?
No, it's not hyperbole. In fact, it might be an understatement. If I can walk into your lobby or slip into an empty conference room and I plug a rogue laptop into a wall jack.
Just any old wall jack.
Any wall jack that hasn't been hardened, I am effectively bypassing your firewall. I'm not hacking through the wall. I'm already inside it. The switch just trusts me.
So let's break down this default state. What does a fresh, out-of-the-box switch actually look like that makes it such a risk? Because I think most people assume default means safe.
Not in networking. Default means compatible. First off, every single port on that switch is administratively up.
So if you buy a 48-port switch and only use 10 computers...
Those other 38 ports are live wires, just waiting.
Waiting for a connection. Then you have this DTP mode.
Dynamic trunking protocol.
Yeah.
By default, it's set to dynamic auto, which, it basically means the switch is sitting there saying, hey, I'm willing to be a trunk if you are.
So it's actively trying to form a high-level connection.
With whatever plugs into it, yes.
Yeah.
And the trust level is just unrestricted. It assumes whatever plugs in is legit.
Okay, so that's the problem. A device that is way too friendly. Let's start fixing it. The research structures this in layers, which I like. The first layer is what they call port hygiene.
Right. Layer 1, the physical stuff.
And the advice here is almost frustratingly simple. It just says, shut it down.
It's the simplest security control in existence, and yet it's the most overlooked. If a port isn't being used, it should be disabled. The command is literally just shut down.
So you go into the interface range, say ports 8 through 24, and just kill them.
You kill them. So if you're the attacker in the lobby and you plug into one of those ports...
I get nothing.
Nothing. No link light. The attack surface physically vanishes. It's like trying to open a door that has been bricked over.
Okay, but we can't shut down everything. People have to work. So the real challenge is securing the active ports. This is where the source material gets into a threat called M flooding.
This is a classic noisy attack. To understand it, you have to understand how a switch thinks. A switch is smarter than a hub because it has a brain, a memory bank called the CAM table.
The content addressable memory. It's the contact list. It knows who lives where.
Exactly. It knows M address A is on port 1, but that list has a limit. It's physical memory. So in an MC flooding attack, the bad actor uses a tool, a source M MAC generator, to just bombard the port with thousands of fake MS addresses.
They're spamming the contact list.
They were filling it up with garbage. And here is the critical failure point. When that CAM table hits 100%, the switch panics. It suffers memory exhaustion.
So can't learn anything new.
And it enters what we call fail open mode.
Fail open sounds bad. You want things to fail closed, right? Like a secure door that locks when the power cuts.
Exactly. But a switch prioritizes traffic flow. So when it fails open, it reverts to being a dumb hub. It takes the data meant for the CEO or the finance server, and it floods it out of every single port.
So the attacker sitting in the conference room just has to listen.
And capture the stream. They're suddenly seeing everyone's traffic. The switch has stopped keeping secrets because its brain is full.
That's terrifying. So how do we stop the flood? The source points to port security configuration.
This is the shield. You have to tell the switch, do not learn unlimited MC addresses. You go to the interface, set it to switch port mode access first, Then you enable port security.
And you set a strict limit, like a bouncer at a club.
Exactly. A maximum of 1 or 2 MZ addresses is plenty for a user, a PC, and maybe a phone. If a third MS shows up,
The bouncer stops it. But how does the switch know which 2 MS to let in? The notes list 3 methods: static, dynamic, and sticky.
static is the manual way. You literally type in the MSC address for every device.
Which sounds like a nightmare.
It's totally unscalable. You'd never do that. Then you have dynamic. The switch learns the MAC when a device plugs in, but if the switch reboots, it forgets everything.
So we want the third one, sticky.
Sticky is the Goldilocks solution. It learns dynamically, but once it learns that NZ, it saves it to the running configuration. It sticks to the port.
So even if the switch reboots, it remembers port 5 belongs to Bob's laptop and nobody else.
Exactly.
Okay, so we've set the limit. Now what happens when the attacker breaks the rules? The source lists 3 violation modes: protect, restrict, and shutdown.
This is a big debate. Protect is the weakest. It drops the bad packets, but it doesn't log anything. It's silent.
Like a bouncer who just quietly pushes you back but doesn't tell anyone.
Right. Restrict is better. It drops the traffic, sends a syslog alert, and ticks up a counter. So your monitoring team actually sees a red light.
But the default and the most secure is shutdown.
The nuclear option. And for a fortress architecture, it's the best. If a violation occurs, the port shuts down instantly. It enters an error-disabled state.
It effectively dies.
It dies. And the recovery is key. It requires an administrator to manually log in, type shutdown, and then no shutdown to bring it back.
I like that. It forces a human conversation. You can't just say, oops.
Exactly. It turns a silent attack into a loud operational problem.
Okay, let's move up the stack. We've secured the ports, but now we need to talk about slicing up the network. This brings us to VLANs and VLAN hopping.
And this takes us right back to that dynamic auto setting. Remember, the switch is willing to form a trunk with anyone. A trunk link carries traffic for all VLANs.
So if an attacker can trick the switch into thinking they are also a switch,
They get access to everything. They can jump from the guest VLAN to the server VLAN.
the research mentions a technique here called double tagging. How does that work?
Okay, so a normal packet on a trunk has one tag, like a colored sticker, that says which VLAN it belongs to.
VLAN 10, VLAN 20, and so on.
Right. In a double tagging attack, the attacker crafts a packet with 2 stickers. The outer sticker says VLAN 10, the one they're allowed to be in. The switch sees that, strips it off.
And underneath, there's another sticker.
A second sticker that says VLAN 20, the secure one. The switch just blindly forwards it along.
And this only works because of a quirk called the native VLAN, right?
Exactly. The one VLAN that doesn't use tags by default. This confuses the switch and lets the hop happen.
So how do we stop it? The source outlines a 5-step strategy. Step 1.
Kill the negotiation. Switch port non-negotiate. Tell the switch to stop asking to form a trunk.
Step 2. Hardcode the ports.
Force every user-facing port into switch port mode access. Make it impossible for them to become a trunk.
Step 3 is interesting. Secure unused ports in a parking VLAN.
This is the digital void strategy. You create a VLAN, say VLAN 1000. That goes nowhere. No routing, no servers. Put all your unused ports in there. So even if someone enables a port by mistake, the person who plugs in is in a dead end.
I love that. The parking VLAN, steps 4 and 5 deal with that native VLAN issue.
Right. Everyone knows the default is VLAN 1. Hackers know this. So step 4, shift it. Change the native VLAN to some random unused number like 999.
And step 5.
Explicitly tag the native VLAN traffic. This closes the loophole in the logic that allows the double tagging exploit to work.
Okay, so we've locked the doors and reinforced the walls. Now let's talk about identity. DHCP and ARP. The source mentions 2 flavors of DHCP attacks.
DHCP hands out IP addresses. The first attack is starvation. It's a denial of service.
With a tool called the Gobbler.
A very descriptive name. It generates fake mantees and just requests every single available IP address. It eats the entire scope in seconds.
So when a legitimate user tries to log on,
The server says, sorry, I'm sold out. No IP, no network access.
that's bad, but the second flavor sounds worse. Spoofing.
This is a man-in-the-middle attack. An attacker sets up a rogue DHCP server. When your computer boots up, it shouts, I need an IP.
And the corporate server usually answers.
Right. But the rogue server answers faster. It wins the race. Your laptop accepts the IP configuration from the bad guy.
Why does that matter? Who gives me the IP?
Because the rogue server also sets itself as the default gateway. Every email you send, every password you type, it all goes through the attacker's laptop first.
And port security can't stop this because the attacker's using a valid MAC. They're just lying.
Correct. So we need a new shield. DHCP snooping.
This sounds like we're eavesdropping.
We are. We're turning the switch into a traffic cop. You configure the ports leading to your real DHCP servers as trusted. They are allowed to hand out IPs.
And all the user ports are
Untrusted. They're allowed to ask for an IP, but if they ever try to offer one, the switch drops the packet. It kills the rogue server instantly.
And that solves the starvation attack, too.
With rate limiting, yes. You add a command, ITDHCP snooping limit rate 10. It tells the switch to block a port if it sends more than 10 DHCP requests per second. No human does that.
Now, there is a hidden benefit here. DHCP snooping builds a database, right?
Yes, the binding table. This is critical. As the switch watches legitimate transactions, it takes notes. It writes down AMC address A, received IP address B on port C. It builds a verified map of who is who.
And that map enables our next security feature, dynamic ARP inspection, or DAI.
Right, because without DAI, ARP is the Wild West. It's how devices find each other, but it's stateless. It has no memory. If I just announce, hey everyone, I am the router, your laptop just believes me.
The blind trust problem again.
Exactly. But with DAI enabled, the switch acts as a bouncer with a guest list. And that list is the DHCP snooping binding table.
So when an ARP packet comes in from a user port,
The switch intercepts it and checks the list. Does this IP and MAC match what's in the binding table? If yes, the packet goes through.
and if it doesn't match,
Drop it and log it. You're not on the list. It completely neutralizes ARP spoofing.
it's a real ecosystem. You can't have DAI without DHCP snooping.
Layered defense.
Yeah.
One feature feeds the data for the next.
Okay, one final segment. Protecting the topology itself with spanning tree protocol. The source calls the threat King of the Hill.
Spanning tree prevents loops in your network. To do that, it elects a root bridge, the king switch that directs all traffic.
And the king is elected based on...
The lowest bridge ID. It's a race to the bottom. That's the vulnerability.
So an attacker brings in a rogue switch, sets its priority to 0.
The lowest possible number. They plug it in and send out superior BPDUs, which are basically election ballots.
And the rest of the network sees this priority 0 and says,
All hail the new king. The network reconverges around this cheap device under a desk. All traffic now flows through the attacker.
it's a massive man-in-the-middle position that probably crashes the network anyway.
It almost always does, so we need to read the election. The mitigation is speed and shields.
Speed being PortFast.
PortFast. You put this on user ports. It tells this is a computer, not another switch. Skip the election and just turn on.
But the shield is BPDU Guard, the panic button.
Exactly. You enable it on those same user ports. The logic is simple. A computer should never send a BPDU packet. Only switches do that.
So if a port with BPDU Guard sees a BPDU,
It knows a rogue switch has been plugged in, and the response is immediate. Kill the port. Error disable it. It protects the kingdom by sacrificing the port.
I love the ruthlessness of it when configured correctly. So we've gone from this open, trusting, vulnerable state to a fortress architecture. Let's do a quick recap.
Sure, it's a SAC. Layer 1 is physical. Admin shutdown on unused ports. Layer 2, data link. Port security. Limit ARMACs. Use sticky. Stop the flugs.
Then layer 2 topology, BPDU Guard to protect spanning tree.
Layer 2 VLANs. Lock down your trunks. No DTP. Hardcode access mode. Move the native VLAN to 999.
And finally, layer 2 logic, DHCP snooping and DAI. Build that trusted map of your network.
It really reinforces that final quote in our source material. Security is not a product, but a process of layering defenses.
By securing the edge, you protect the core.
That's the key takeaway. You can have the most expensive firewall in the world, but if your edge switches are sending spoofed, double-tagged traffic right past it, you've already lost. The edge is the new perimeter.
So here is a thought for you to carry with you today. Look at the wall jack in your office right now. Is it administratively up? If you walked over and plugged in, would you get an IP address, or would that port shut down and send an alarm to the security team?
It's a question worth asking your network admin. Nicely, of course.
Or maybe check the config yourself. That's it for this deep dive into Layer 2 security. Thanks for listening, and stay secure out there.
See you next time.